thank you all for coming out tonight for the second seminar in our three-part series, Water's Journey. My name is Chris Piccone from Ashburnham. I'm an ecology professor at Fitchburg State University and a member of the board of directors at the Nashua River Watershed Association, or NRWA. In case there are a few of you who may not be very familiar with the NRWA, a little background, this nonprofit was founded in 1969 to clean up the Nashua River, which at that time was one of the 10 most polluted rivers in the United States. Those early pioneers, including our hero, Marion Stoddard, who is here with us tonight, they created a model for what would later become the Federal Clean Water Act. Today, the NRWA continues to work on water quality, as well as environmental education, stormwater management, land protection, and nature-based solutions to adapt to climate change. Our speaker tonight is Sarah Whiting, who joined the NRWA Board of Directors in 2021. Sarah is a senior water resources engineer at Interfluve, a small design firm that focuses on ecological restoration. Sarah is a native of central Massachusetts and currently lives in Shirley on the banks of the Squanicook River. Sarah has a bachelor's degree in civil engineering and a master's in water resources engineering from Tufts University. Prior to venturing into ecological restoration, Sarah focused on hydraulic and flood modeling and mapping, dam safety, and stormwater design. She has about 10 years of experience volunteering for the town of Shirley's Planning Board and Shirley's Stormwater Committee. Plus, of course, she's on the board with us at NRWA. To finish her biography, Sarah adds that she likes to travel with her teenage son, who has turned out to be the best kind of travel companion. She also enjoys riding her road bike, preferably uphill. Oops, 1 second. Sorry about that. And this winter, Sarah adds that she's taking full advantage of the cold weather by taking up Nordic ice skating, conquering Lake Champlain, Lake Sebago, and the Swedish archipelago. So with that, Sarah, I'll turn it over to you.
Thank you, Chris, and thanks everybody. Welcome to the third talk in our webinar series. As Chris mentioned, my name's Sarah. I'm a civil engineer by training, a water resources and restoration engineer by practice, and a lover and hopefully a good steward of this beautiful earth by choice. And tonight I'm going to talk about what can be quite a grim topic about the impact that humans have had and are having on our rivers and streams. And before I get too far into the presentation, I would really like to thank the members of the Climate Impact Committee, present and past. I took full advantage of the brain trust in developing this presentation tonight. These topics that we're covering here are enormously complex and nuanced, and we do our best to synthesize and summarize vast bodies of knowledge to make it accessible and concise. And no doubt we have people in the audience tonight who are experts in topics that will be either casually mentioned offhand or maybe not mentioned at all, but that are perfectly relevant to the topic. So as much as each of us might like to think that we can know everything, no one has the entire picture themselves. It takes a functioning ecosystem of community. And here we have a community, this community, our community, to come together to listen, to learn, to converse, and to share ideas. And through this togetherness, we can build a better view and understanding of our environment and our place within it. The work is never done, as Marianne likes to remind us. So tonight, I'd especially like to thank Wynn and Ryan, professionals at the NRWA, for preparing and providing in-depth content and for herding us cats to get us here tonight. I'd like to thank Warren Kimball for his vast library in his mind and on paper that seems to include the entire history of water research in our region. And of course, Ralph Baker, Bob Pine, Chris Piccone, Michael Watkins, and Dave Armstrong, active members of the Climate Impact Committee, for their comments, contributions, and feedback. And then CIC members of times past, which include Elizabeth Ainsley Campbell, Sue Edwards, Mike Fleming, Martha Morgan, Lucy Wallace, and Joan Watkowitz. So thank you, and I will begin the presentation. If I can, there we go. Before I get into it too far, I'm going to give our discussion a little bit of context so that we can keep track of where we are and how things relate to each other. Because the nature of this topic could be full of doom and gloom. Like, for example, if we were to focus this presentation completely on global climate change by indirect means, we might quickly be overwhelmed at our powerlessness. But we are not powerless. So we're going to mix it up a little bit. We're going to explore human impacts that are direct, like point source discharges, and indirect, like burning fossil fuels that change the atmosphere, that increase the Earth's temperature and everything that follows from there. We're going to talk about changes to the atmosphere. We're going to talk about changes to water quantity in our rivers and streams, changes to water quality, and we'll get just a slight taste of changes to ecology and habitat and vegetation and wildlife. We will explore human impacts at the global level, but we'll also look at the impacts at the regional and local levels. And then I'm going to throw you a teaser of hope, because next month, the third talk in this series will feature local actions and local initiatives by the NRWA and other local organizations that counteract the effects of climate change and all the other, not all, but most, and as many as they can, the other negative impacts to our watersheds. So these actions that our local organizations are taking to help maintain and enhance the resilience of our ecological systems, they give our environment the strength and resilience to weather any other incidental disturbances that may occur in the short, medium, and long-term time horizons. So we look forward to hearing from Ralph and Bob next month. Stay tuned. All right. I want to give you a brief introduction to some of the most comprehensive, authoritative resources that we have at our disposal to educate ourselves about the state of knowledge in climate science. There's been so much misinformation force-fed to us through mass media for decades, like for my whole life, really, that when I talk about climate change and I use those words, I have a little bit of fear. And I'm not even really sure I realized I had this fear until I had a eureka moment a few years ago when I participated in an international program for women in hydrology. The first speaker in the series was a woman from Sweden, and she gave her presentation while walking on a treadmill. It was evening for her, and she was factual and unapologetic about speaking about the climate observations and research and conclusions made through her institution and her research. And I realized, like, oh yeah, there are parts of the world that don't have to deal with the coded language and censorship and retaliation related to climate science. And I just wanted to acknowledge that if we know less about the topic than we want to, it's not because we're not smart or curious or interested. It's because we've been conditioned to be afraid of it, and possibly rightfully, because cuts to our research institutions, NOAA, the USGS, et cetera, based on words, continue to force us to change the way we talk about these things. So, but let's be clear. The Federal Highway Administration and the armed forces have been anticipating and planning for climate change for decades. Their internal policies and their external documents may use coded language, but the leadership isn't stupid. Our military institutions see a threat and respond to it. So if you look closely, you may find some of the most progressive responses to climate change in those surprising places. So let's get into the state of the science. And here I'm going to introduce you to the IPCC, the Intergovernmental Panel on Climate Change. I'm going to tell you a little bit about the organization, who they are and what they do, and then we'll touch on the context of their work. They don't just amalgamate and synthesize climate studies. They interpret the results of those studies so that we and our governments and our policymakers can understand how climate change will affect the things that are critically vital to our global civilization. And then finally, I'll summarize their findings on water on the global scale, because my talk is, after all, about water. But it's worth a mention that 2 months ago in January, our government stated its intention to withdraw from the IPCC, among other groups and collaborations associated with the United Nations. However, the work of the IPCC is ongoing, and information will continue to be available for as long as the UN exists. So what is the IPCC? It's a United Nations body for assessing the science related to climate change. It was established in 1988 to provide world leaders and governments with regular scientific assessments on the current state of knowledge about climate. It provides a framework for collaboration between government scientists and IPCC staff. And it produces reports that provide a balanced and comprehensive assessment of the state of knowledge on topics related to climate change. The people who participate in the IPCC, they read all the research and they evaluate it and collate it and summarize the findings into a very easy to read report. It's accessible to everybody. It's very impressive. And if you haven't taken a look at it, I recommend that you do. The sixth assessment report was issued in 2022, and there's a link on this page. And one of our CIC members reminded us that it's worth noting that the IPCC was jointly awarded, along with Al Gore in 2007, the Nobel Peace Prize for their efforts to build and disseminate greater knowledge about man-made climate change and to lay foundations for the measures that are needed to counteract such change. The IPCC reports interpret the science and report on how the changes to climate will affect critical elements of our civilization, things that are super important to us on a global scale: agriculture, energy, water use, drinking water, sanitation, urban areas, freshwater ecosystems, water-related conflicts, human mobility and migration, and cultural water uses of Indigenous people. And chapter 4 of the report is all about water, and it summarizes their findings on the global scale. And the IPCC's findings related to hydrology and water are: the science says all components of the global water cycle have been modified due to human-induced climate change. Satellite data clearly show that precipitation patterns have shifted worldwide. Some areas will have more or less annual or seasonal rainfall. Some areas will have more extreme storms and more prolonged dry spells. And some areas will have both. They'll have more extreme storms separated by longer dry spells. Changes in soil moisture are detectable in the satellite data. Changes in ice distribution are detectable in the satellite data. And spring seasonal groundwater recharge has been reduced due to shorter snowmelt seasons. But groundwater levels are still mainly affected by withdrawals for agriculture and domestic supplies. Data supports the conclusion that extreme weather events have been made more likely by human influence on climate change via greenhouse gases. So that's what the global science is telling us. But what does that mean for us here in New England? We have, for our region, we had the National Climate Assessment Project led by the U.S. Global Change Research Program. This was a U.S. program. It was initiated in the 90s under the Global Change Research Act, which required working groups consisting of government agencies and research institutions to publish updates every 4 years. In 2025, the federal government cut off funding and dismissed the experts, so the reports are no longer available on the project website. They are still available online as published and distributed by former partnering agencies. And as recently as this week, I was able to find the 2023 Fifth National Climate Assessment. So it's still there. And right now it's online at toolkit.climate.gov. Chapter 21 of that report gives us a summary of their findings for the Northeast US. And the report says that their findings show precipitation in the Northeast has increased in all seasons. Extreme precipitation events have increased by 60%, which is the largest change in the US. You know, the largest changes are here up in the Northeast. The number of days in the Northeast with extreme events has increased. Urban and flash flooding has increased. They report that the frequency of droughts has decreased, which I think is, counterintuitive, because I think we've experienced some droughts here, and that they found that heat waves are lasting longer and are more severe. And while our talk today doesn't specifically address oceanic or marine climate change, because we're talking about rivers and streams, this report concludes that ocean warming and marine heat waves and sea level rise and ocean acidification are occurring, and they're changing the distribution, productivity, and seasonal timing of life cycle events of living and marine species. Some of those marine species migrate into our rivers and streams to complete a portion of their life cycle. And if the timing of our thawing changes, and if our insects are emerging early or late, and if the timing of our spring flows change and affect the timing of some of the migration of these species, these mismatches, these new desynchronization will harm specific components of our ecosystem and our entire ecosystem as a whole. And moving down to the smaller scale, we also have local resources to help us understand climate change here at our local level. And for this, I'm going to present information available through our own organization, the Nashua River Watershed Association. As Chris said, for many, many years now, our environmental professionals here have been observing, studying, and documenting local impacts of human influence, not just the nebulous, indirect, and intangible, like global impacts, but the direct impacts. And remember, it's here at the local level where we can, we think globally, but we act locally. We can make the biggest difference. This is where we have the power to heal the natural environment and increase its resiliency from disturbances. And in doing so, we increase our own resiliency in the face of change. Over the years, the Nashua River Watershed Association has observed, documented, and released comments and information on the impacts to water. They've released information related to flooding, droughts, erosion and sedimentation, warming temperatures, and water quality. And the NRWA has also observed and documented and commented on impacts to ecology, including landscapes, invasive species, changing seasons, declining species, aquatic habitats, and impediments to adaptation and migration. And furthermore, they haven't just commented on it. The NRWA has programs in place to address some of these issues at the local level. Stay tuned for next week's presentation. We're going to focus on water, but this is a good reminder that water is not just the end of the story. The story is really about life, and water is one of the requirements for that. So now I'm going to change gears a little bit. That was a little like documentation heavy, but we're going to spend a little bit of time talking and thinking about rivers before we spiral into the doom and gloom of all the harms that we cause our natural environment. So let's spend a little minute here reveling in the glory of that which is river. What is a river? We have to ask this question first. We have to understand what it is that we're trying to protect and preserve when we concern ourselves with the health and function of a river. Query your imagination and consider the simple question: what is a river? Easy, right? I mean, we usually think of it as a longish, thinnish body of fresh water, fresh moving water confined to a channel. Maybe it starts high up in the mountains. Sometimes it starts in glaciers. But maybe it starts up in the hills and descends in cascades and pools as a babbling brook. And sometimes you just might miss the origin. That's just a swamp. No, that is the birthplace of a river. Rivers flow downhill, collecting more and more water until they meet the ocean. And so far, we've been fixated on the water, but is a river just the water? Is it not also the channel and the earth material that confines it in place, or that would confine it in place if it's doing its job and hasn't been harmed by people or other things? And here I want to take a little aside to tell you that the earth is actually, the earth meaning the land and the soil is actually pretty bad at holding the river in place. Rivers are always looking for balance. They're a balance between the forces of the moving water and the material that confines it in place. And it's a constant battle between erosion and deposition. And this balance is shifting all of the time as the flow in the river changes. So these pictures here, it's an overhead view of the Saco River in Conway, New Hampshire. And on the right, we have a pretty recent aerial photo of the river with the farm fields and the forested banks and the sandbars and the houses and the scenic railroad and the roads. And then over on the left, we have a graphic presentation of the river's history and potential future. The dark blue band, that's where we typically find the water flowing today. If you went tubing on the Saco, that's where you'd be, in that dark blue ribbon. But if the White Mountains get a little bit of rain, watch out, things get interesting really quickly. The lighter blue flow paths show historic channel scars and potential future flow paths. The river is always adjusting within that valley. And in this location, that river valley is hundreds, like maybe 1,000 feet wide. So woe is he or she who puts their expensive infrastructure nearby, thinking that dry ground or high ground means it's not part of the river. This unnaturally straight line on the bank was a historic attempt to prevent the river from eroding into the wastewater treatment plant. But the river is looking for a way. It hates straight lines. So when a river decides to change its course in a moment, the consequences can be instantaneous and catastrophic, especially if you're in an area where the underlying geology is primarily sandy soils. And we have that in our watershed. We have a lot of rock and cobble too, but we do have sandy soils. And this is a shot of the bank profile along the Suncook River in Epsom, New Hampshire. From this bank, we can gain a little bit of insight into what holds the river in place. It's not necessarily the earth material, it's the vegetation. And this exciting and instantaneous change in the path of the Suncook River happened during the Mother's Day flood of 2006. And the river ended up cutting off and changing course, and it left about a mile of riverbed completely dry. It was probably initiated or exacerbated by a nearby gravel mining operation, taking just one or two more bucketfuls of gravel than the river valley wanted to give up. So that, it was human influence did contribute to that significant event. Back to vegetation, in particular, trees are very effective at holding the banks in place. We know wood is a good building material and we use it all the time. Riverbanks get to use the building material and they get to remain alive. Like they don't have to cut it down to use it. They use it while it's alive. This photo gives us a glimpse of the awesome hiding places that would normally be underwater, providing shade and shelter to frogs and turtles and muskrats and fish and salamanders and mussels and other insects. But this photograph shows Trapfall Brook in Ashby, Massachusetts, a tributary of Willard Brook and the Squannacook River. The brook went dry in 2022, so you are looking at a completely dry riverbed. So we're going to come back to this photo later when we talk about droughts, but we're going to stick to vegetation for one more minute. The vegetation that flanks our rivers and streams also influences the water available to our ecosystems in other ways. Here's a photograph of the stream in my front yard during the spring flows before leaf out. And our first accounting might suggest to us that vegetation depletes. The image on the right is now just a couple of days after leaf out. Our first accounting might suggest that vegetation depletes the groundwater. And as soon as the trees and the undergrowth start drawing the water levels in the stream drop. But the really neat thing is that as soon as the leaves come out, the humidity in the air completely changes. Vegetation has a larger role in our biosphere. It helps maximize life everywhere. So those trees and the leaves are moving the local surface water and groundwater into the local atmosphere, making that water available to other life nearby that's not in or adjacent to the stream. It's making the water available via roots and the fungal mycelial network, but the evapotranspiration changes the relative humidity and produces the morning dew, which provides just enough water for the small germinating plants and spiders and insects. Like that morning watering supports small-scale ecosystems. And zooming back out to the global scale, vegetation can create the local weather that sustains some of our largest river systems. I'm not going to go into it here, but relatively recent research into the phenomenon of the biotic pump. It's a theory about how forests create their own self-sustaining weather. And this research evaluates, among other things, the big rainforests and river combinations like the Amazon and the Congo, where the forests and the rivers act together as an inseparable pair. That's one of the manifestations of the ways that biology on the planet drives self-balancing, self-sustaining, self-healing ecosystems, even in the interiors of vast continents where moisture is not readily available because it's so far away from the ocean. But the key is that these processes working in synchronization, they're inseparable. They only work as long as we don't interrupt that intricate balance that holds them together. And here's kind of where we arrive at the big bummer of the evening, where I start talking about all the things that we do inadvertently sometimes to upset that balance. So one of the biggest indirect impacts that humans are having to our natural environment, not just to rivers and streams, but to the entire planet, involves greenhouse gas emissions and the greenhouse effect. The five primary greenhouse gases are carbon dioxide and methane, water vapor, nitrous oxide, and ozone. And these gases have always been present in our atmosphere. They're natural. But with the discovery of oil and the advent of industrialization, we've been releasing more of primarily carbon dioxide and methane to the atmosphere. Carbon dioxide from burning fossil fuels and methane from livestock production. Nitrous oxide and ozone become more important at regional and local levels. They constitute smog in cities. The atmospheric data collection station at our lab observatory on Mauna Loa in Hawaii has been monitoring carbon dioxide in the atmosphere since the 1960s, and it's pretty clear from this image that there's an increasing trend. More greenhouse gases in the atmosphere means more heat from the sun is trapped during the day and retained during the night. And the greenhouse effect results in the warming of our air, land, and water. Here's the climate spiral animation by NASA's Scientific Visualization Studio. It'll probably loop a couple of times. The animation presents the average monthly temperature time series from 1880 to 2022, and it demonstrates a warming trend spread evenly throughout the year. And yes, there's a correlation to the increase in carbon dioxide. So what does that mean for water? Well, a warmer atmosphere holds more water. And remember, water vapor is also a greenhouse gas, so it's a positive feedback loop, but not in the positive way we're hoping for. An atmosphere saturated with water is likely to produce more severe storms with more precipitation. And this goes for storms with both a small footprint and a large footprint, like, for example, local summer thunderstorms, but also massive hurricanes. And a warmer atmosphere is also a thirsty atmosphere. And a thirsty atmosphere will steal water from our surface waters, our soils, and our vegetation, and hold it and retain it in the atmosphere where it's not available for life. It will change the dynamics of relative humidity and morning dew. And without that morning dew, we're more likely to see flash droughts and crispy, flammable ground cover, which leads to wildfires. Thankfully, not so much out here, but definitely out west. The interactions between climate change and human response are infinitely complex. I found this messy tangle graphic that shows a feedback loop for how climate change, you don't need to read it. The really important thing here is that it's a mess. It shows how climate change impacts to rivers and streams, water, those are the blocks in blue, will affect people, those are the blocks in green, and require a response, those are the blocks in white, ultimately leading to increased use of fossil fuels in red, which will increase the magnitude of climate change impacts on, rivers and streams and water, back to blue. So it's a feedback loop. It's very interdependent. There's too many things to talk about. In this talk tonight, we're really only going to mention water quality, water quantity, and touch on land use changes. We're going to dabble a little bit in transportation and ecology, but it's so complex that to have one talk about all these topics and interdependencies would be impossible. And I hope that this can be part of the conversation later. I'm sure there's people online tonight who can specialize and talk about individual things that we missed tonight. So for our own sake, we're going to simplify, and we're really just going to get to 3 or 4 elements. And I'm going to use the metaphor of a table with 3 legs, which doesn't make a very stable table, but we're going to go with it. And we're going to talk about water quantity. This is what I know best in a traditional sense. We're going to talk about water quality. And on this topic, I'm going to draw from the brain trust at the Climate Impact Committee. And we're going to talk on river form, although just lightly tonight. And lastly, and maybe most importantly, I've just described 3 characteristics that are subject to the laws of physics and chemistry. But physics and chemistry happen on every planet in our solar system, in the universe. You change a few coefficients, change a few constants, rerun the numbers, and you can predict flood flows on Mars. What makes us special? Well, we have life. We have habitat, wildlife, ecology, biology. Life affects our natural systems, and our natural systems affect life. They provide a buffer and balance. They make our rivers and streams resilient and self-healing. So We can't leave plants, animals, fungi, bacteria, algae, etc., out of the larger discussion. So now we're going to go into the legs of the table and head on through. Let's spend a few minutes exploring how local, regional, and global impacts are showing up here in our local stream flow record in our watershed. At the global and regional scale, we've been told by the experts that we should expect to see increases in total annual precipitation. We should expect to see increases in total annual flow in the Nashua River and its tributaries. We should expect to see increases in the magnitude and frequency of flood events. And interestingly, it's suggested that we should see a curious decrease in droughts. But what does our information tell us? And to make sense of our analysis, let's first take a moment to understand how water enters and leaves the Nashua River watershed. If our system was simple, it would simply be that more rain would equal more runoff, would equal more flow in the river. That's an easy analysis. But our watershed has some special features, some special inputs and outputs that we should know about. So rain falls on the Nashua River watershed. Some of it runs off into our rivers and streams, and some of it percolates through the soil and becomes groundwater. Some of it evapotranspirates back into the atmosphere, and that's normal. That happens everywhere. Sometimes we withdraw water from the ground via wells to provide consumptive and non-consumptive water for our homes and our businesses. Some of that water ends up back in our sewers and is treated at the wastewater treatment plants and released back to the rivers. And some of that water ends up in our septic systems where it percolates back into the ground. But our watershed is also part of one of the best planned water supplies for a city anywhere in the world. We have the Wachusett Reservoir located in our watershed, and that can be, we could consider that a headwater of the Nashua River. But that's one major stop in a system of interbasin transfers across the state and across the region. We're connected by aqueduct to the Quabbin Reservoir, which is filled by the Swift River, a natural tributary to the Connecticut River and ultimately Long Island Sound. We're connected to the aqueduct to the Ware River, another tributary that flows to Long Island Sound. And we're connected by aqueduct to Boston, which naturally drains east to Boston Harbor. We have water flowing into and out of our watershed, 30 miles in one direction, 70 miles in the other. It's pretty incredible. And I'd like to thank Dave Armstrong for this slide on interbasin transfers. This slide provides some solid details about the history of the Wachusett Reservoir. But in summary, this slide shows us that, reading that last bullet, in a hydrologic sense, the Wachusett Reservoir effectively isolates 115 square miles of the Nashua River watershed. And the minimum releases from the reservoir to the South Nashua River are relatively small, only about 20% of the river's natural flow at that location. So a big chunk of the headwaters are cut off from the Nashua River proper as we think about it. And now that we know a little bit more about how our watershed works, let's look at some data that the USGS has been collecting for the past 90 or so years. And let's ask this data a few questions. So the question I want to ask is, are we seeing more water in the Nashua River on an annual basis? The USGS keeps about 9 gauges in the watershed. We're just going to look at 4. 3 on the main stem of the Nashua River and 1 on the Squanicook River, which is a relatively rural, pristine, uncontrolled tributary. And let's look at that map for a second. The Nashua River flows from south to north. The big gray area is the part of the watershed that drains to the Wachusett Reservoir, and we're going to ignore that for this. We know that water's going somewhere else. And we have gauges on the North Nashua River from upstream to downstream. We've got the gauge in Fitchburg, we've got the gauge in Leominster, and then we have the gauge in Pepperell up close to the Nashua, New Hampshire border. And then we have the Squanicook River off on the side. And now let's look at these graphs, which you don't need to read everything. I'll get to the summary so that you don't have to worry about the data itself. The black dots and the black line represent the average daily flow in a given year. And the x-axis is the year. And from left to right, it goes from about 1925 to 2024. And the red line represents a trend. And if you take one thing away from seeing these graphs is that a red line sloping up to the right indicates that the stream gauge record indicates that the river is seeing more flow on an annual basis as time goes on. So what do we see here? At our pristine gauge, the Squanicook River, the graph over on the right, the line slopes up. And at our most downstream gauges, Leominster and Pepperell, the line slopes up. And at our most upstream gauge in Fitchburg, the line is pretty flat. It slopes down a tiny bit, but it's not necessarily significant. And these data suggest that for the most part, the data in our watershed shows that we are seeing more water in our watershed on an annual basis. That's consistent with what the reports are telling us we should be seeing. Now, I think there's something different going on in Fitchburg, and we should take some more time to see what the data might be showing us. And if I were to keep going with the next step in this analysis, I'd try and figure out, if it's because the Fitchburg gauge has less data, or is urbanization making a difference? Are there more well withdrawals or reservoirs, or is there more impervious area making a difference in these measurements? But this makes a great research project for a student in a hydrology class or an environmental statistics class. So if you're interested, or if you have a student who you think might be interested, send me an email after this is done. This is it's a great little research project or a school project for anyone who's interested. Now let's talk about flooding for a minute. And to whet your appetite, here's a picture of the 2010 flood event on the Nashua River. This is a view of 110-2A looking from the Airtown line up into Shirley. The experts tell us that the frequency and magnitude of storms is supposed to increase. But my question for today is, are floods getting bigger? Let's look and see what our local data tells us. Oh, another picture of the flood. It was pretty impressive. Oh, and more pictures. This is at Neshoba Paddler. So are the big floods getting bigger? This graphic attempts to answer that question. Are the single biggest annual floods getting bigger? The black dots and lines present the peak flow at the respective USGS stream gauges in a given year. And exactly like our last slide, if the line slopes up, then the annual peak floods are getting bigger over time, or at least that's what the data is suggesting to us. And if it slopes down, then the peak floods are not getting bigger. And, if you're looking at the data a little bit and you see those big spikes in the black lines, early on in the graphs, those were the hurricanes and the significant weather events in 1936 and 38. Those are the storms of record for the region. We haven't seen anything that big since then. So here the data seems to show us that at our rural Squanicook tributary, the answer is yes, the peak floods are getting bigger. And at our upstream gauges in Fitchburg and Leominster, the answer appears to be yes. But at our most downstream gauge in Pepperell, the answer is like, nah, they might not be getting bigger. The answer might be no. And this is an interesting finding. Floods are bigger in some parts of the watershed, but not in the watershed as a whole. And this suggests to me that peak floods from intense storms and rainfall might not be watershed wide. It would take a really big watershed wide storm or a massive watershed wide melting snowpack to result in a remarkable peak flood at the most downstream gauge in Pepperell. And that the rain events that cause the floods might have a smaller footprint. They might be local to specific tributaries. If they were caused by a summer thunderstorm, for example, this would make a lot of sense, like that 11-inch 6-hour storm we saw in Leominster a couple of years ago. A storm like that is really, really small. It has a really small footprint, and the precipitation is focused in one drainage path. So what's my conclusion here? Are peak floods getting bigger? I'm feeling a little bit mixed about it. The trend appears to be increasing, but the size of the event matters. So now let's talk about observations on droughts. We've had some pretty bad drought years recently, especially out west. I queried the US Drought Monitor at www.drought.gov to show our local historical drought record, from about the year 2000. And according to the monitor, our area has experienced extreme drought 4 times in this period of record, which is about 26 years. And all 4 of these extreme droughts have occurred since the second half of 2016, so in the past 10 years. And notably, 3 of these droughts have occurred since 2020. We saw drought in 2020, 2022, and 2024. But I'd like to mention and remind you that, like, you may remember that at the end of 2023, through the spring of 2024, we had a lot of rain. Many parts of Massachusetts experienced the wettest monthly rainfalls on record. So we went from remarkably dry to remarkably wet, back to remarkably dry. And remember how I said earlier that a warmer atmosphere is a thirstier atmosphere? It can hold more water and release more water, but that water has to come from somewhere. So the rapid cycling between intense wet and intense dry, it's got a name. It's happening. It's being observed in other places. It's called climate whiplash, and we can expect to experience more of it if these warming trends continue. So let's look at some of the pictures of what the 2022 drought looked like in our neighborhood. This drought map represents the conditions in about August 2022. Most of the Nashua River watershed was in a state of extreme drought. And we've seen this photo already tonight. This is Harris Brook in Ashby, the headwaters to Willard Brook in the Squanicook River. It was bone dry. It was very easy to survey, but that didn't make us very happy. The Cold River at the DCR Mohawk State Forest was also mostly dry. You drive over this river if you head into the state park to go camping. If you like to go tubing on the Deerfield River, like at Zor, for example, this is the tributary that comes in when the Deerfield River swings close to Route 2. Here's the picture of the West Branch Mill River in Williamsburg on the Williamsburg-Goshen town line. You can use the moss on the rocks as a gauge. Usually the water is lapping at the moss. It usually looks like this, but it was dry. And then here's Bear's Den in New Salem, a trustee of reservations property just north of the Quabbin Reservoir. Typically in the summer, this section is a series of cascades and pools. It's great for cooling off. It's so much fun. It's very beautiful. It was not flowing. There was a sad little trout in the puddle who tried to hide under a rock overhang. So the fish and the crayfish and the water-dependent animals, they can't adapt to this. They can't adapt to no water, and they've got nowhere to go. So there's no temporal continuity to these rapid swings in habitat. Here's what it looks like when there's water in it. So what does our stream flow data from the USGS tell us about droughts in our watershed? This series of figures tries to answer the question, are the annual summer low flow drought flows getting lower? And that's not every question you want to ask about drought. You might want to say, like, are the flows staying lower longer? You might want to know you really might want to know for a particular river or stream, there might be a threshold flow below which, it's functionally empty. But this series of figures tries to answer one specific question. The black lines and dots represent the lowest 7-day average flow for a given year, and a red line sloping down suggests that the data supports the conclusion that low flows are getting lower. So our data appear to show that low flows are getting lower in our urban areas in Fitchburg and Leominster, but not on the Squanicook River and not on the Nashua River in general at Pepperell. So remember how our regional climate change resource said that we would see a decrease in droughts. These results here suggest to me that drought conditions might be very local. They might be affected by lots of things unrelated to lack of rainfall. There are other things that affect drought conditions, urbanization, impervious surfaces, and groundwater withdrawals. And the state of, statistical analyses to identify droughts in the record aren't as established as floods and daily flows. So do I have a conclusion here? I'd say that I don't, but I think if, there's another student of hydrology who wants to spend some time looking at the data, I think it's a good project. And to attract the nerds, I'm just going to flash this figure up on the screen, but I am not going to talk about it. Water quality. The second leg in our stool table. Um, let's spend a few minutes now attempting to understand the tangled and interconnected, interdependent, messy impacts that we have, both direct and indirect, on water quality. For me, trying to organize this topic was like playing one of those old children's games, Kerplunk or Topple, or like what comes first, the chicken or the egg? Like, where do we even start? Because everything's connected. So, first, I'm going to start by reading you an excerpt of the work from the previous Climate Impact Committee. This excerpt describes, in general, the anticipated impacts of climate change on water quality, and then we'll tease apart elements of and talk about those in more detail. So here's the quote. Multiple adverse impacts on water quality are anticipated due to climate change. Warming water temperatures may mean the loss of some cold water fisheries in the watershed. Higher total rainfall and more severe storms may increase suspended solids and turbidity due to scouring of stream beds and erosion of their banks. More acid rain can be expected, lowering the pH of the water and increasing stress on aquatic life. Increased loadings from non-point source pollution, including pollution from more distant sources, can be expected. And this may include increased nutrients, pesticides, and bacteria from rural areas, metals, oil, and grease from urban areas, and salt from highways. Older cities with combined sewer systems can expect more frequent overflows to the river, bringing increased turbidity and bacteria. Lower summer flows and less dilution will make point sources of pollution more pronounced, and the combination of warmer water temperatures and increased pollution will lower dissolved oxygen levels that are necessary to maintain aquatic life. So all that being said, with our discussion of water quality tonight, we are going to limit the topic a little bit and talk about point source pollution, non-point sources of pollution, temperature, dissolved oxygen, erosion, sedimentation, silt, and turbidity, and nutrients. And we're going to talk about these in the context of our watershed. So first, what is a point source? We can think of this as a pipe outlet. It's a source of pollution that you can easily identify. Like, where is that nasty stuff coming from? It's coming from here. One of the most obvious, direct, and appalling impacts people have on rivers relates to point sources. Back in the 70s, the Nashua River was considered biologically dead. Low dissolved oxygen caused by the industrial discharges and raw sewage suffocated most of the complex organisms, almost all of them. The river bottom was coated with toxic sludge from the paper mills. The water was chocolate milk, or, looking at these photos, it was a red velvet mess. The photo on the right is, before, and the photo on the left is what we see today. It was teeming with pathogens and sewage, and fish and insects couldn't breathe, and they had no place to lay their eggs. The river was fundamentally dead. These are the legendary photos that accompany our local movement to protect rivers and streams. Over the past 50 years, people have come together to stop this and to prevent it from happening again. Since the original photo, the nasty photo, was taken, we've got, as Chris said at the beginning of the talk, we've got the Federal Clean Water Act. We've got the Clean Water Act here in the Commonwealth and all the supplementary laws and regulations that go along to support that. And we've got local initiatives and public support in town government and our nonprofit organizations like the NRWA and ORS, and other regional organizations. And furthermore, I think here in Massachusetts and New England, we have the public expectation that there are people like us in our many different capacities courageously, and it does take courage, to make sure that our natural environment stays in good health. So with respect to these point sources, humans were the problem. Humans are the answer. And we're brilliant and we can do anything we put our minds to. And we're strongest when we work together. It's really important for us to remember that we have the power to fix these problems. In the grand scheme of things, the point sources were the easy ones. They're relatively easy to handle. They're direct impacts and they're easier to identify and they're easier to remedy. But many of the other things that we do to harm our rivers and streams are indirect and part of that interdependent, messy feedback loop. So where do we jump into that loop? Well, Tonight, we're going to start with temperature. Higher temperatures can be caused by direct or indirect means. You can have a discharge from a power plant putting out hot water. But there are some things that people do inadvertently and unintentionally that also lead to warmer water. And those things include urbanization, paving roads and driveways and parking lots. That does a couple of things. Runoff from the surfaces in the summer is really hot, but also that impervious cover prevents infiltration of rainwater and reduces the availability of groundwater, which maintains a cool average temperature, somewhere in the 50s around here. And we also like to clear our vegetation and our trees that would normally provide shade over the water bodies and keep them cool. And we pump out groundwater for municipal and industrial uses and reduce the amount of groundwater available to replenish our rivers and streams through springs. So if we combine a few bad things, lower low flows, longer droughts, we have less water in our rivers. And when we deplete those cold groundwater springs, the temperature of the water increases. And when we have record-breaking warming in our winter and our summer months, the temperature of the water increases. And why is this a problem? Why do I have pictures of the fish on this page here? Warmer water holds less oxygen. Many of our charismatic aquatic species here, for example, our trout and our salmon, they need cold, highly oxygenated water or they suffocate. And if they can't get to cold, highly oxygenated water by traveling up or down a river because the river is dry, or another problem we haven't talked about yet is because we've put barriers in place. If they can't find cold, oxygenated water, they die. And then they rot, and then we see that on the news or we smell it. Warm water also increases the frequency and intensity of algae blooms, especially if there's excess nutrients in the water. Algae blooms change the pH of the water. They end up reducing dissolved oxygen. They consume the oxygen in the water. They decrease light penetration. It's a negative feedback loop. Everything conspires together to make the conditions worse and worse for complex life. So we just listed a bunch of keywords. We use words like urbanization, paving, clearing vegetation, withdrawing groundwater, building roads and bridges and dams, discharging industrial effluent and sewage. All those actions have consequences, and they result in an increase in runoff and dirtier runoff and warmer runoff and lower oxygen. We create barriers to passage. And then, as a consequence of these things, there's an accumulation of toxic substances, and we end up with bacteria and pathogens in our water. But as we've grown and matured in our understanding of the human impacts, our federal, state, and local laws and regulations have created water quality standards and water quality report cards. So we monitor for these adverse outcomes, and we have processes in place to start to address them. And for this part of the presentation, I'm drawing on the Brain Trust. And a lot of this information comes from Warren Kimball's body of work at Mass DEP. And if I could put in a request for a future presentation, I would love to hear him describe his experience in the evolution of Massachusetts' journey towards improved water quality through the decades. He knows most of the answers. If I misspeak tonight, I'm going to ask Warren for help. So this slide summarizes a very brief summary of the history of water quality and issues in our watershed. Since the 70s, actions that we've collectively taken have resulted in massive improvements in water quality. In the 70s, point sources were the biggest problem, industrial and municipal, and we handled those and improved water quality by about 20%. And in the 80s, the biggest problems were a little less big. Efforts shifted to controlling urban runoff, disconnecting the storm drains from the sewer pipes, fixing septic systems, and eliminating pollutants. We started to handle those and improved water quality by 50%, about. And then in the 90s, the biggest problems continued to be the combined sewer overflows, bacteria, turbidity, legacy in-stream toxicity, and nutrients. But note that the problem is shifting. As we eliminate the sources and we allow time to go by and nature to do its work, the problems become more and more compatible with life. Things aren't dead, they're just living differently. And today, our biggest battles continue to remain, combined sewer overflows, nutrients, legacy toxic substances, and some of the impacts of urbanization in the upper watersheds. Every year, the National River Watershed Association deploys a veritable army of volunteers to collect data and to share it with us, river report cards, so that we can have up-to-date information about water quality, real time sometimes. It's important to collect this data so that we can identify any one-off or really bad conditions that might be happening. Um, but it's really wonderful. They also let us know when our rivers are safe for fishing and for swimming. In 2025, in particular, the water quality monitoring program included testing and reporting on bacteria levels like E. coli, which is what I have up here. We don't want to swim in water with high levels of E. coli. We'll get sick. Um, they collected data on dissolved oxygen. We love high dissolved oxygen. It means our fish and our other organisms can breathe easy and survive. They collected information on temperature and also on conductivity, typically used as a surrogate for salinity, which can reflect, road salt, for example. These report cards are used by the local, state, and federal officials to make decisions about policies and actions, as needed. I use the report cards to check and see if I can go out back and swim. There are some great swimming holes on the Squanicook River and all around the watershed. We are really lucky. And this information keeps people safe and helps us take action to protect our ecosystems. We still have and will probably continue to have problems related to excess nutrients for quite some time. In freshwater systems, the problem nutrient is typically phosphorus. And the funny thing about phosphorus is that it loves to bind to soil and silt. So combined with increases in erosion and increases in deposition at places where this material gets trapped, if soil drenched with fertilizer washes away and ends up in our waters, impounded behind a dam, for example, it's going to feed algae and nuisance plants for a really long time. Sometimes on the order of a century. Phosphorus is really, really tightly bound to the sediment. That's just the way the chemistry of phosphorus is. But one way we can reduce phosphorus over time is to stop the contributions to our water bodies. And this will require controls and limiting contributions to our land. And another way to remove it from our system is to harvest the plant matter and the algae, to take it out of the water mechanically and use it for something else, which is something that we also do here in our watershed. We have programs to harvest the plant matter. Specifically, in our watershed, we harvest the water chestnut biomass at the Pepperell Dam impoundment. So that's that annual work does two things. The primary reason might be invasive species control, but it is also taking excess phosphorus out of the system and improving the nutrient conditions. My advice here is specific to stormwater runoff. We'll see more if we have more precipitation and if we have more severe rain events. But my advice specific to stormwater runoff doesn't relate to water itself. It relates to controls to land. Under natural conditions, a lot of stormwater runoff, wouldn't exist. It would percolate into the ground and infiltrate into the soils and become cool groundwater. But because we like to pave surfaces and smooth out our land and lawns, we end up with stormwater runoff. So it's our job to do our part to avoid adding more nutrients to rivers and streams by reducing stormwater runoff and reducing fertilizer and pesticide application to our land. It also, stormwater runoff also includes a lot of the things that come off of our roads and our cars, like fuels and grease and the debris from our tires. And I think, clean water starts with protected land. You've got to protect the land to protect the water. And we need to protect the land from erosion. It doesn't take much to trigger erosion, and it doesn't always take much to prevent it either. So let's appreciate this exposed soil profile for a moment. This is the bank of the Squanicook River at the Bertozzi rope swing on the Shirley side. Here's it's a densely forested sandy riverbank, and we see a very thin needle duff layer on top and a foot or two of fine grained gray sand. And below that, we have many, many feet of rich orange brown sand. And we can see the roots of the trees and the mountain laurel. And let's appreciate how any disturbance, like even bare feet, I mean, this erosion, the erosion of this bank is caused by bare feet. It can initiate and set off significant impacts. Like the bank is held in place by the tangle of roots and the vegetation. And without the vegetation, the bank's gone. It's not gone today, but it's on its way to being gone. And it makes it much more vulnerable to erosion by other things, more intense rainstorms and high flows in the river. And now, two more things to talk about. I know it's 8 o'clock and when I'm just about done. Let's talk about some of the things that we build intentionally that can create barriers along our rivers and streams. They don't always, but they can. We build a lot of roads. These roads cross our rivers and streams. And to make our roads work, we build a lot of bridges and culverts. This map shows over 2,300 intersections between our stream and road networks. Sorry, New Hampshire, I didn't download the mapping data up there. So there's more than 2,300, but 2,300 in mass. So within our watershed, we have potentially 2,300 interruptions to continuity along our waterways. The longest contiguous stretch of any river or stream is pretty darn short. So this fragments that aquatic habitat and prevents the migration of species when they need to find a safe space if conditions are going bad in their particular, location. Imagine for a minute if we fragmented our transportation network like this. Like imagine from your house in your driveway, how far can you drive before you pass over your first little bridge or culvert? And now imagine that you can't. For me, I could probably go 100 yards. I wouldn't even get out of my driveway. And so now realize that in a lot of cases, that's what our fish and our salamanders and our turtles and our wildlife experiences. Some stream crossings are fine. They're transparent to our rivers and streams, and they're designed and function in a way that they don't create obstacles. But a lot of our stream crossings are undersized and they get in the way. So what are we doing to solve this? The NRWA's got a program to start looking at this. For the past 2 years or so, professionals have been leading the charge in culvert assessments and training assessors in other watersheds with huge success. And they're helping prioritize culverts to be replaced to provide more habitat continuity. It's a long-term project. Assessment is the first step. And in the future, we can expect to chip away at these barriers and replace them with bridges and culverts that are no longer barriers. That's going to take an army of people and a lot of collaboration between the towns and the state agencies. We also interrupt our river systems when we install dams. We have, I think, almost 300 dams in the watershed. Some are for flood control, some are for hydropower, some are for recreation, and some are just obsolete relics of times gone by. So over the past 11 years or so, the Mass Division of Ecological Restoration has been stewarding dam removal programs. There are some active dam removal projects, and the status of those projects ranges anywhere between early reconnaissance and exploration, to design and to permitting. And some projects in the watershed have been completed. We know that dams block the movement of water, and to a degree, but they also interrupt lots of other transport processes, and that can have a negative impact on water quality. They trap sediment that's moving downstream with the water, and that sediment gets deposited behind the dam, and all the nasty pollutants and fertilizers, they stick to it. PCBs and PFAS also bind to sediment and can concentrate and accumulate where sediment deposits. The water behind the dam is warmer because it's typically unshaded and it's moderately stagnant. And because it's full of nutrients, it's great for algae growth. And then the algae growth consumes the oxygen in the water, which in turn suffocates the complex organisms. So it creates that negative feedback loop. And all that fine sediment settles on the natural substrate that would have lined the bottom of the channel and would have provided habitat for fish and for insects and other life forms. So it's 8:06. My presentation is drawing to a close, but I'm missing a discussion of the huge topic. I've only just peppered in references to it. It's missing a full discussion of human impacts to the ecological web of organisms that depend on our rivers and streams. It's missing a specific discussion of the animals, the fish and the mammals and the birds and the insects and you name it, the plants, the fungi, the bacteria. This series is titled Water's Journey. But if I could put out a request to the Climate Impact Committee, and I think I can, to commission a talk on the impact of climate change to the ecology of our watershed, that is something that I know I would like to learn more about. Approaching this topic or this problem as an engineer, sometimes I feel like I approach the problem from the bottom up, like I'm focused on a solution to a perceived problem that someone else has identified. But you can't identify the problems if you don't know how things are supposed to work in the first place. And I think that's one of the reasons why we do so many inadvertent, unintentional things that harm our natural systems. Like I said at the beginning, there's too much for one person to know. It can be really complicated. And even if the information is available, it could be inaccessible, or, maybe we just haven't heard it in a way that arrives, in understanding within us. Like perhaps if someone different said the same thing in a different way, it would reach us and we would know what to do. Our curiosity and our interest are vitally important, and continuing efforts for education and understanding are paramount. So what I'd like to say is thank goodness we've got people here at the Nashua River Watershed Association and in our audience tonight and in our communities who give their attention to identifying and solving these problems and educating us and reminding us how things fit together. We create these improvements and provide this quality of life for each other. So thank you very much for coming tonight, for your curiosity and your interest. And as Marian always reminds us, the work is never done. So thank you.
Thank you,
And
Sarah. It's awkward not to have an applause. There we go. We got some applause coming online. We've got a few minutes for questions and chat with this group. We've got a lot of experts here. I guess I could do a quick summary that while you were talking in the chat, there was a lot of chatter people had about the importance supporting what you're saying, the importance of mature forests and large trees to do some of the functions you've been talking about and to meet our climate goals. Bill Mumma was referenced a few times, so if folks are interested, read the chat. One comment was about the drought affecting the Quabbin Reservoir, reinforcing what you were saying. So if people have new questions, you got a couple options. You can put your question into the chat at the bottom if you want, or alternatively, if you want to speak to the folks, either to answer a question that comes up or to raise a question, you go down to the heart symbol at the bottom of your screen. It says react. If you click on that heart symbol, you can raise your hand and we'll try to get to people who want to speak with the time we have. I'll just throw out one question that was posed by Win of NRWA that could you just quickly explain why culverts interrupt wildlife passage?
well, I'll go back to the picture of the culvert on Harris Road here. And this particular culvert is just a corrugated metal pipe that's punched through underneath a road. And you'll notice that it is set up above this is the downstream limit of that particular culvert. And you'll see it's like creating a little waterfall into the pool downstream. And what that has done, it does a couple of things. If there's a fish downstream in that pool, it can't swim, it can't necessarily jump into the culvert and move upstream. So that's a barrier right there. But if you were a salamander or a turtle, you couldn't reach it either. A functionally transparent stream crossing will provide both a continuous stream bed from upstream to downstream. It will provide a continuous bank so that your salamanders and your turtles and your, semi-aquatic but bank-loving animals can move upstream. But ideally, and it's, the Cadillac, the gold standard of a crossing would be where in the top line of this particular figure, where you have a bridge that just has a few piles in the middle, but it spans the entire floodplain so that your megafauna like your deer and your moose can also stay next to the river and move up the riparian corridor. So, there's different degrees of barriers to passage. Um, Ideally, you would pass your terrestrial wildlife, your bank and amphibious wildlife, and your aquatic wildlife. But, you do what you can with your budgets.
Well,
Did that?
if others have comments on the culvert question, pipe in now. Otherwise, a different question was posed, and I'm going to ask for help from other members of the NRWA board on this one. But the question was about the pros and cons of removing the dam at West Groton, and and I assume the question is, what would NRWA's position be on that? And I know there was a formal statement that came up to the board that we agreed to. And other board members can correct me, but I think the gist of it was there are a lot of ecological benefits of removing dams for reasons Sarah pointed out. But there are also dams that have a lot of important cultural value to that local community. And you need to listen to the local community. And if the local community supports removing a dam, well, then an RWA would clearly support that for the ecological benefits. Does that catch the gist of the statement? I see some more the chair and other board members nodding, I think. So feel free to
Um,
pipe in. Okay.
I think right. It's the community decides, and the role is to provide information to support, but every dam has, a special is evaluated individually. There's no blanket preference to take any course of action.
Okay. And I think of maybe a final question, a couple from Sue Edwards on the topic of small farms, or I guess any farms, polluting the water with their manure. And a lot of farms resent any kind of government regulation. So, what recommendations would folks have to keep those nutrients out of the water?
I mean, I would say, agriculture doesn't have the same sort of like legal requirements to take action to prevent runoff. But if you were, wanted to do the right thing and keep your nutrients on your land, which is where you want it, it doesn't do you any good if it's runoff and into the water body. You want the phosphorus and the fertilizer and, the nutrients from the manure. You want to keep that for use. Um, there's a lot of low impact type ways you can do. I mean, you can cover it. You can put it in an area that's a little bit contained, so that it's not subject to rainfall and runoff. Um, you don't have to do anything technologically complicated. Sometimes it's as easy as just letting a little bit of dense plant growth, grow on the buffer between the edge of the fields and the river. So, those
Yeah, I
buffers
think
do
I've
a lot
seen
of heavy lifting.
statistics like even just like a 12-foot buffer removes the overwhelming majority of the phosphorus and nitrogen that would otherwise run off. Yeah, another nature-based solution. If anybody else wants to pipe in, does anybody here have expertise on manure management or farm pollution? Uh,
Wynn's got her hand up.
oh, I can't see the hands raised. Go ahead.
oh, and it's not about farm pollution. You mentioned flash droughts, which
Mhm.
I feel like is a new concept I've just heard of in the last few years, and I'm curious if you could describe sort of what that means, a flash drought, and I'm also wondering what happens where you have lots of rain and then you have a flash drought. Like, how does anything adapt to that?
Well, we don't really have many species that are adapted to that sort of rapid varying condition. That hasn't been necessarily like a New England and a Northeast, climate situation. But I mean, actually, I suppose we could say it's only been 12,000 years, right? Since we had our big glacial movement, right? So I guess I would ask if anybody knows if there are any other habitats on planet Earth that have those rapid fluctuations. I think the flash droughts would come because we have higher temperatures and maybe periods in the summer without rain. There might be plenty of water in the groundwater table, but it might just be we haven't had rain for a while and the humidity has dropped, and then everything dries out and gets crispy. Doesn't take long. Oh, I see Garth Fletcher. They have their hand raised. You're welcome to speak, but remember you're on mute right now.
Okay. Yeah, this is Liz Fletcher. I recently was looking at a table of buffers, research. It's a New Hampshire table, but research from all over. And I was surprised to hear Chris 12 and a half feet because the conclusion from generally all those different researches over the last 20 years or more was that you need to get rid of 60% of the pollutants. You need 100 feet minimum.
Oh,
And so I don't know, maybe the 12 and a half feet is just phosphorus and nitrogen, but it doesn't seem enough, you know? I don't know. Maybe Chris has a more recent study, but this
no,
is like
actually, but my data was from a very old study, and I can't remember even where it was done. So don't quote me on that. I'm pulling it out of my brain from something I thought of a while ago. I would say you also have to balance with the farmers are going to try to maximize what they can get out of the land, and so it's all a balance. And
I know.
but some is better than none, and more is better than some. So
But if they can give up 50 feet of
true.
space, they're probably protecting themselves more from flooding and scouring and all
Yeah.
that stuff too.
And
So,
that's where subsidies could come in.
mhm,
Maybe the town is interested in payments for ecosystem services. But, yeah,
good.
So I would say, when I think about the farmers adjacent to the river, and I go back to the Saco River example that I gave, if you allow a forest to grow up alongside of the river, then you might have more success holding it in place. Um, you lose your farmland if it all washes away too.
yeah,
That's actually a problem they've been having at the World Farmers Farm down in Bolton Flats, where they
yeah.
have major erosion. They're right at all these bends in the river, and of course it floods through there in the spring, and they've been trying to figure out how to protect those banks, and they've done some work with culverts to move water around, but it's a big problem down there for the farmers.
Mm,
The problem with, large wood as a bank stabilization feature is that it takes a long time.
mm.
Um, but it's effective.
So in the chat, we do have Michael Watkins had posted some UMass advice for containing nutrients and manure. You can see that there. Somebody had posed a question about a bill S 2836. I'm not familiar with that one. Yes, in my backyard. Does anyone want to try to speak to that? Or otherwise, I'd have to say we don't have that. Certainly NRWA doesn't have an opinion on that because not that I've heard of.
Yes, my backyard appears to bypass or overrules local zoning. Oh, it's housing.
Does
It's too.
anybody know? Isn't it? I mean, that for decades we've had the 40B program where you can bypass everything except everything except the local wetlands bylaw, or is it everything except the State Wetlands Protection Act, I think. But so 40Bs already provide dense housing, low income housing where you can override a lot of local regulations. Oh, go ahead, Renee, you have a hand up.
Yes, hi. This is a new law that's being proposed statewide to overrule any kind of zoning and bring things down to the 10,000 square foot house lot level. It was brought to my attention by Paula Terrasi, our
Huh.
conservation administrator in Pepperell. And it would be, it's not like 40R where you're designating a certain area where construction is going to be concerned. It would be townwide, statewide. So it would just basically overrule all zoning. That's what it appears to do.
Hmm.
Um, so I'd be curious to see whether NRWA could take a look at that and see what they think about it, the law that's being proposed and any impacts.
Well, I see some board members taking notes, so we'll we'll look into it.
Yeah, and as far as manure management, so I'm on the Board of Health in Pepperell, and we are working on a livestock and manure management regulation. We have modeled it with a template using Carlisle's regulation. And it, I think that in a lot of towns, there are guidelines, and our town had guidelines for, manure management, but there wasn't anything that had any teeth to it. So what we wanted to do was put everything together under one regulation that calls out the Wetlands Protection Act, the watershed, um, the Aquifer Protection Zone, to have, manure being managed properly so that it's not either within the 50-foot buffer zone of the wetland,
Hmm.
or at least it's, you know, it's going to be managed in a way that it's not going to be going toward the wetland. So that's all that's going to do. And there will be a permitting for that for farms that are not commercial, because in my research, MDR actually licenses commercial farms. So they look at their plans and they go on site to make sure that they're doing things properly. And that's not happening with the smaller farmers. So yeah,
Okay.
I think there aren't that many towns that have actually a regulation as opposed to guidelines.
Okay, thanks.
Yeah.
Oh,
On that messy slide of all the interconnections, there was a whole section on that sheet about the social elements like housing and land use and all that stuff too. Like all of this stuff comes together. It's such a complicated problem. Like how do we balance all the things that we need with our protections for our environmental, systems? It all matters. It all works together, hopefully in a good way, but sometimes we make a mess. We don't mean to. I believe that. I believe we don't mean to.
well, would Win or Ralph or Bob, would you be willing to state the title of the presentation in 1 month, to maybe things we can do to help clean up the mess?
When I when I think you probably have access to that more readily than I do.
Or even the topic?
Well, the topic is on our what we can do about these problems, and it will focus on the use of nature-based solutions, which is something that the NRWA has been working on along with our partners. So return, and you'll hear all about it a month from now.
Yep, I think it's titled Nature-Based Solutions to Protect Our Natural Hydrology. So, this is based on observing how nature works and then working with nature to use it, kind of recreate or protect its own systems to have things work the way we want to. As Sarah says, everything's all wound together and coming up with solutions that get us where we want to be.
Great. Well, that seems like a good point to close up, do you think?
Thank you
All right
very
then.
much, everybody.